Hello everybody. In this video we're going to be covering one of the sections in chapter 5 of our text, molecules and compounds. In this video we're going to learn about representing molecules as chemical formulas. So we've learned that a compound is a distinct substance that is composed of atoms of two or more elements. To describe a compound, we're going to describe the number and type of each atom in the simplest unit of the compound. Okay, so that might be a molecule or the simplest repeating unit in an ion. Each element is represented by its letter symbol from the periodic table. And the number of atoms of each element is written to the right of the element as a subscript. If there's only one atom, the one subscript is not written. So typically you're not going to see a subscript of 1. You'll just assume that that is a 1. Polyatomic groups are going to be placed in parentheses, and we're going to talk a little bit more about what the polyatomic groups are. So water has a chemical formula of H2O, right? And we're typically pretty used to seeing this. But you may not have recognized yet that this means that there's one hydrogen, or that there's a hydrogen and there's two of them, and then there's an oxygen, and there's an assumed one subscript here. It means it's just one of them. This symbol right here means therefore. So if water is equal to that, therefore 2 atoms of hydrogen, 1 atom of oxygen. Table sugar is going to have the formula C12H22O11. Therefore, it's going to have 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. And it's going to look like this. You can see that as the molecules get bigger and bigger, a lot of very complicated structures are possible. So there's an order that we write the elements when we write a formula. Typically, we're going to write the metals first. An example of this would be like sodium chloride. Sodium is our metal, chlorine is our non-metal. So we put the metal first. Non-metals are usually written in this order, except there are some times when this isn't true. For instance, here we do have CO2, so we're following this order of carbon first, then oxygen. But sometimes we deviate from that, really, for like historical reasons. For instance, we do write H2O, but we also write sodium hydroxide, where we have the oxygen coming before the hydrogen. So don't get too caught up on the order, but in general, it's good practice to try and put them in this order. Let's do a little bit of practice here. Let's see if we can write out a chemical formula for hematite. If I tell you that it's composed of 4 oxide ions for every 3 iron ions. And let's see if we can write out acetone. If I tell you that the molecule contains 6 hydrogen atoms, 3 carbon atoms, and 1 oxygen atom. I'll give you guys a moment. So if it has 4 oxide ions, that's 4 oxygens, and 3 iron ions, that's 3 irons. So we're going to write our metal first. We're going to put a 3 there. And then we're going to have our oxygen, our non-metal, and put 4. Acetone, we're going to go in the carbon, hydrogen, oxygen order here. And we're going to have our 3 carbons, 6 hydrogens, and 1 oxygen atom. So polyatomics are certain groups of atoms are bonded together to form what is called a polyatomic ion that acts as a single unit. Okay, so basically what happens is for some atoms we're going to have a situation where they like to stay kind of stuck together in a stable configuration, and you're not going to see these typically break up, and they move around as if they were a single atom. And there's a list of them. It's in table 5.5.1 in our text. And it's just one of those situations where you need to learn to recognize these. So when you're looking at a formula, you have to, just recognize these certain patterns and recognize that that is a polyatomic. However, there are some special rules because these are kind of all stuck together for writing them in a formula that can help you to recognize them. So let's take a look at that. So here we have two examples. We have what we call magnesium nitrate, because this is a nitrate polyatomic, and we have calcium sulfate because it's calcium bound to a sulfate. We have an implied 1 subscript on both of the metals here, which means that we're saying that there's only one atom of magnesium and one atom of calcium. You'll note that over here we have no parentheses around our SO4, so we do, just in the context of this, have to recognize that this is a sulfate ion. Over here, though, we do have these parentheses, and what we're saying here is that basically we have two of these nitrate groups, okay? And we can't just simply put a 2 subscript because there's more than one symbol here. So you can kind of see why the parentheses are necessary if we're going to treat this like it's one unit. What that means that we need to do is we need to recognize that in order to get a count of the atoms here, okay, we need to multiply all of the values on the inside by this value here, okay? So a single nitrate has 1 nitrogen and 3 oxygens. But because there's 2 of them, there's going to be 2 nitrogens and 6 oxygens in magnesium nitrate. Over here, where we don't have the parentheses, it's exactly the same. It operates exactly the same way as you would predict it to. You have 1 sulfur and 4 oxygens for your atom count. So let's try a little practice here where we're going to determine the total number of atoms or ions in one formula unit of each of the following. So we have magnesium acetate. This is the acetate polyatomic. We have 2 of them. And then we have mercury phosphate with 2 of the phosphate groups. So try and make an attempt to identify how many of each atom we have and then the total number of atoms in both of these. Okay, so in this example, we have 1 magnesium. There's a implied 1 subscript there. We have 2 times 2, 4 carbons, 2 times 3, 6 hydrogens, and 2 times 2, 4 oxygens. If we add that all together, we have a total of 15 atoms. For our mercury phosphate, we have 6 of the mercury atoms. We have 2 times 1, 2 phosphates, and 2 times 4, 8 oxygens. If we add them all together, we got a total of 16 atoms in this molecule.